So it should just be Jack and Porter online today. Let's see who we got. So, so where did we leave off last time? We were talking about branching and linking, if memory serves, yes? Okay. Huh? Yeah, with the PowerPoint. Okay, so um, branching or branching with linking, right, are basically how you do subroutine calls or loops. And um, so let's just start writing some stuff and see what we get. Uh, so let me start a new project here in Genie. Um, and let's see, project new, close that project. We'll call this one, I don't know, loops one. And then I'll make a new file and we'll just call this main.asm. So we don't technically have to call everything, or sorry, the main routine main, um, but uh, except that GCC kind of expects that, uh, which is what we use to link and kind of finish putting the executable together. It's not the only way to do it, but it's it's a convenient because GCC is something that we use for C compiling anyway, and B, as we'll see today, maybe Thursday, we'll start to use some functions that are built into C, namely the functions for um, printing things to the console, scanning in user input from the keyboard, things like that. And since those are built into C anyway, then we kind of have to use the C libraries for that. So we'll just use GCC to link everything. Um, okay, so let's start by writing something that has a loop. Um, well, what's something we could write that has a loop? I mean, lots of different things, right? Let's come up with something. What was the very first thing that we did? Yeah, we did the triangular numbers. Okay, I don't want to do that because that's going to be an assignment, is to redo that, but in ARM. Okay, so why don't we do sort of a really stupid loop, which is just to count up, right? So 1 plus 1 plus 1, however many times. So this would be like the world's stupidest multiplication. Um, all right, so what's going to be in our main um, thing? Well, first off, so what do we want to do? So let me actually write this sort of up in C for a minute. So we'll sort of comment all this out. And comments I think are percents. No, what is comment? I don't remember. I never put comments in here. No, that's not a comment. That's actually part of the program. Uh, it depends on the language. So, okay, whatever. I'll just delete this when we're done. But what basically I'm going to do is write something that's like for int I equals 0, or how about let's start with 1, I less than or equal to 5, um, this sort of thing. Okay, and then we'll just add I to itself each time. Okay, kind of stupid, but whatever. Um, and so this would be my loop body. So I'd say I'd also have like int n equals 0, and then do something like n equals n plus um, n plus 1, say. So just add 1 to itself a bunch of however many times. Okay. So yeah, silly program. Not going to do much, but that's okay. It'll get us the idea of looping. Okay, so to do this, what I want to do is, well, first off, I need to load a couple of numbers, right? So what numbers do I need to load in this case into some registers? I need to load the number 0 because that's going to be sort of my counting variable, or I mean the total. And then I need to load the number 1, which will be my counting variable for the for loop. I also need to load what else? 5 or 6, or depending on how I want to do it, right? So I could load the number 5, I could load the number 6. Which one I pick just depends, like, do we want to do tests on less than or equal to, greater than or equal to, right? Which test do we want to use? Okay. Um, so there's that. So let's just start loading things. So first off, what do we need to do? We need to do move. Uh, let's put 0 in x0. Let's put 1 in x1. And let's put 5 in x2. Okay, that's fine. Okay, and then let's we'll put our loop body here, and we'll call it loop. Okay, and then in the loop is where we'll do the actual loop stuff. Okay. Um, and what is it that we want to do in our um, loop? And actually, I guess we technically don't need this because, and the reason why is so if we have, let's see, which way do I want to do this? Well, okay, there's a couple of ways we could structure this loop. So in this case, the program is definitely going to enter the loop, right? And then the loop will branch to itself to do itself however many times, okay? After the loop is complete, the program is done, right? So actually, no, you know what I do want to do? Let's go ahead and do this. When we come back from the loop, what do we do? Hmm? So when the loop's finished, then what? Then we're done with the program, right? So we can just return. Right. So, well, sort of. I mean, that this idea of a label is part of pretty much any assembly language. Um, so what will happen is when we assemble this, okay, um, the loop stuff will be some sequence of instructions. Those are going to get slotted into memory someplace. And then the assembler is going to say, okay, loop's first instruction is in memory address something, say 17. Okay. Well, it has to be a multiple of 4, so let's say 20. Okay. Um, and then it would replace where it says B loop. Okay, that's going to be a branching instruction, but a branching instruction needs to be passed a memory address, right? So the assembler would say, oh, well, loop starts at memory address 20, so I'll, in the branch instruction, replace the memory address with the number 20, and then the thing will know where to go to, okay? Um, okay, does that make sense? Yeah, okay. Um, all right, so what is it we want to do in our loop? Well, we're just adding the number 1 to the number 0, and then continuing possibly the loop, right? Okay, so what do I need to do first? Well, let's just add x0, x0, and x1. Okay, so that's adding here the number um, 1 to the number 0. Okay, then what? It already is in register 0, but yeah. Yeah, we need to check, have we hit 5 yet? Okay, we need to compare which registers. We need to compare x0 with x2. Okay. Uh, no, because, well, okay, that's going to be up to us. Where are we putting the sum? Where did I choose to put it? X0. So, um, so actually, I guess we technically need two. Uh, you know what? Let me go up and change this to that. Um, so, because otherwise, we would actually need to use another register to to start at 1, and another and 1 to start at 0. So we would need 4 of them. But yeah. Uh, no, because this I'm going to think of as the one that I keep adding each time. Okay. Um, yeah. Okay. I see your point, guys. So actually, you know what? Let's do this. Let's um let's use here. Let me just put in some comments. We'll put that in x0. We'll put this in x1. Put that in x2, and we'll put the number 1 in x3. Okay. So let's put that there. I'll put it back to 1 just for the sake of demonstration. Um, okay, and then we'll go down here and we'll add x0 and x3, and then we'll also add there. Okay, so what this will do, right, is we have two things that we're keeping track of. We're keeping track of the running total, which we'll put in x0, okay? And we'll also keep track of our counting variable, which we're going to, so this will be the letter I, right? The variable I, I'm just going to stick in x3. And then the number that's in x1 will stay as 1 all the time. And that's the one that I'll use to add to stuff. Okay, so which registers are going to change their values here as we run this program? 0 and 3 will change, but 1 and 2 will stay constant. Okay, is that all right? Yeah. Who are we missing? Go ahead. Oh, I'm sorry. Yeah, that's what I meant. So sorry, 0 and 1 are changing, 2 and 3 aren't. So the register 1, I'm going to think of my counting variable I, and register 3, I'm just going to use the constant, the number 1, and just leave it there for use. Okay. Okay, sorry, I said it backwards. Okay, so my counting variable, we chose to put in register number 1, right? That's the thing that's going to get 1, 2, 3, 4, 5. And then, so what do I need to do the comparison here with is I need to compare x1 and x2, not x0 and x2. Okay, and I can get rid of that space. All right, now we need to branch to go back and start the loop over again. Under what circumstances do we do that? If we want x1 to be less than or equal to x2, okay? So what this means is that I need to do a branch less than or equal to the loop. Okay, is that cool?
How does it know what you're branching off of?
What do you mean?
So you're saying branch is less than or equal to.
How does it know what's less than or equal to? Well, okay, because remember the branch, or sorry, the compare instruction does what? Sets flags, and the branch instruction reads those flags.
So there's only one set of flags?
Yes. Yes. So, of course, what that means then is if you are doing multiple comparisons, you have to be careful. Um, yeah, go ahead. No, no. Okay, so the it goes with the compare instruction. So the compare instruction, I specify which two registers I want to compare. It compares them, and it sets the flags appropriately. Yes? Okay. The branch instruction says, okay, if the flags are set to indicate the state less than or equal to, then I will branch to the routine called loop. Otherwise, I will just continue. Okay. So the thing that's going to go directly after that is what would happen if we do not continue looping. We're finished with the subroutine. So what do we have to do? We have to go back up to the main program, which means we need a return. Sure. Mm-hmm. Well, okay, there is no less than or equal to flag. Okay, what are the flags? Negative, zero, carry, and overflow, right? And less than or equal to means that the negative or the zero flags are one. Okay, so branch less than or equal to is checking is either the negative flag or the zero flag set. Okay, now if so the branch instruction is only reading the flags, it doesn't set them. Only the comparison instruction here is setting them. So when we go back through the loop and now let's say that we've hit the number 5, the comparison instruction, if let's say that x1 and x2 both have the value 5, um, well, that would be equal to. Okay, so then the next time it would be 6, right? Okay, so is 6 less than 5? No. When it does the subtraction, it's going to have um, uh, which order does it subtract it in? Well, when it does the subtraction, neither the zero flag nor the negative flag will have been set. Okay, so the comparison would update the flags the next time around, not the branching instruction. The branch just reads them, but it doesn't change their values. Okay, which means, excuse me, that if we went back up into the main program and also did some other branching, we would have to make sure to do to reset the flags or do a comparison that would reset the flags before we read them again. Because if we read them without first changing them to be an appropriate value, then we might be branching on garbage information. Okay. Okay. So let's see. Do we have everything we need there? I think so. All right. So let me delete the C stuff that I had there. Hmm? I I don't think it's needed because you're going to be using a comparison probably later anyway. Um, and so it's not really necessary, I don't think. Um, maybe the one exception would be if we were doing something like uh, addition with carry, then we might want to be careful about making sure that the carry flag isn't erroneously set. But uh, odds are there's going to be something like we probably right before we would do an addition with carry would have some other instruction that's going to appropriately set the carry flag. So it's probably not going to matter. Now, it is possible to force reset the flags to whatever you want, right? You can do that. Um, so to clear them, so to speak. But in practice, I don't think we'll probably need to most of the time. Okay, so let's run this thing and see what we get. Um, and hope that I didn't screw anything up. So let's go to our console. All right, and let me make this a little bigger, taller. All right, so we need to go to projects, and then I called this one loops. Okay, so we need to assemble it. So first off, let's just make sure the thing actually runs correctly. Okay, so it assembled correctly, no errors. All right, and then GCC was happy. Okay, and it executed, but there's no output. Okay, so good. Um, Now we want to run this thing through GDB, right, so that we can watch what's happening. In order to do that, if we just did GDB main as is, as you guys probably discovered, what happens? Right? So if I do this, okay, it will run, okay, and uh, here at the very bottom, you see so it says inferior one process, blah, 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 exited with code 05. 05 is whatever's in register 0. Okay, so register 0 by convention is the one that the program exit status is reported to the operating system. And since we were using that and it ended up having the number 5 in it, well, then great. Register 0 had 5 in it when this program terminated. So that will run, and that's fine. But what happens if I try and do something like, right? I start to get errors. Okay, why did I get errors? Yeah, no, nothing wrong with the code. Mr. Lillis, because you figured this out yesterday the hard way. What's the problem? Yeah, we didn't set it up correctly to run GDB. So the code's fine, right? There's nothing wrong with the code. What's wrong is that we have to do, when we assemble it, we need to assemble it with a debugging flag of G. And we need to okay, let me not do that with the pipe. Okay, so I just need to do this with the debug flag set in order to uh, for GDB to use this correctly. Okay, good. All right, so now we can do GDB main. Put a breakpoint at main, run the program. It's going to hit the breakpoint, okay, at the very first line of the program, basically. And then we can start stepping and dumping the registers to see what's going on. Okay, good. So for running it through GDB, you have to remember to put in the debugging flags. Okay. Which, yeah, sorry. I mean, this stuff is kind of technical, right? It's the reason we started off a little slow because, how many of you guys, this is the first time you've ever touched Linux in your life? Probably most of you. Yeah. Okay. And it's not rocket science, but it does take a little bit to get used to. Um, Part of the problem is, well, okay, how many of you guys had ever used a console on your computer before this class, right?
Yeah.
Yeah, okay, that does not count. Well, what are you using the console for in CS:GO other than chat? Huh? Oh, okay. Change your crosshair, kids these days. Yeah. So running the mad hacks. Yeah, yeah, yeah. So okay. Um, no, you've never used a console before, Jack. Yeah. Well, see, this is the problem with you kids these days. Okay. So back in my day, when we had to walk uphill both ways to the computer store in the snow and fight off rabid pterodactyls in the process. We didn't have shoes. We liked it. Um, no. Um, so back in the day, you had to do a whole lot more stuff in the console, right? So the history of OSs over the last 20, 30 years is they've gotten progressively more and more user friendly, and you can do a lot more stuff with the graphical interface now than you used to be able to. Okay. So when I started using computers, so my first computer was a Commodore 64. There was no graphical operating system for that thing. It was the entire machine was the console. That's it. Okay. Then the next computer I remember us having was my dad bought um, it was some sort of like, did we have a 386? A PC, a Windows PC. It's 386 or maybe it was a 486. And um, it came with Windows 3.1. But when you booted up the machine, it dumped you into a DOS prompt, right? So DOS was the operating system. Windows was just a thing that got loaded on top of it. And Windows 95 was actually the same way, right? It was a sort of shell that sat on top of DOS. Um, and so you did a lot of stuff in the console uh, or the DOS prompt, I guess they called it back then. Uh, and so, like, this idea of using the console is sort of foreign to you guys unless you play CS:GO, right? But Yeah. Anyway. All right. Well, let's run through this thing and see what happens. So I put my breakpoint at the very first line, and that allows me to step line by line. If I type continue, basically it would just keep running and just do instruction after instruction. So the step, right? So if I do info registers and we look at the registers, what do we have? Well, register 0 has 1 in it. Did I ever stick the number 1 into register 0? No, and nothing is run yet, right? So this is something that's sort of important to note about registers is that you can't necessarily assume that their contents start out clean as all zeros or whatever, right? So with Brookshire, you could because you reset the machine when you ran it. You can't assume that here. So our registers are full of just garbage, basically. Um, and so it's up to us to start setting them to things that actually matter. Okay, so what are all of these things? Why are they there? No idea, right? Um, and we don't really care. Okay, so but if I now step, okay, so that ran the instruction move x00, and now look what's in register 0. 0, which is what we loaded into it. Okay. Now the rest of the registers are of course still full with whatever garbage that they've got in them. Um, so who cares? Um, and so let's just keep stepping. Okay. And so register 1 now has the number 1 in it as we chose. Um, I should stay here that when I do info registers, the line number 7 has not executed yet. It's line numbers 6 and back that have. So if I do now, register 0, 1, and 2 are set, and register 3 will be set when I step next. Okay, does that make sense? So it's showing you the next instruction, not the current one. Yeah, okay. And let's step one more time. Okay, look at our registers 0, 1, 5, 1. Okay, that's good. That's what they're supposed to be. And what's the next instruction that I'm about to execute is the branch to loop. Okay, all right. Okay, so we step, and now we're inside the loop part of the program. Okay, down at line 12, which is the right here. That's the first instruction that's in the loop subroutine. Okay, and if I do info registers, still 0151. Okay, we haven't actually done the loop body yet. And right, okay. So now let's do step that does one of the additions. Okay, so now what's in x0? 1, because I just added 1 to it. Okay, and I'm about to add 1 to x1 also. Okay, and so now I've got 1 and 2, and then the 5 and the 1 in x2 and x3 are going to stay 5 and 1 for the entirety of this process because we just left them as sort of fixed numbers. Okay, good so far? We do know. We? Okay, so continue A. All right, so we need to step. Okay, so the comparison has just happened, right? And so, and the next instruction that if I stepped again would be to do the branching. Well, this what what does the compare instruction do? It subtracts the two things and sets the flags appropriately. Okay, what flag has been set here? Okay, so this is down on the CPSR. Okay, the end flag has been set. Okay, and that makes sense because I've just subtracted 5 from 1, which is the current value of the counter. Okay, that is in fact negative. And so on the next instruction, when I hit branch less than equal, will I branch? Yes. And that's going to take us back up to the start of the loop, and we'll do this again. Okay, so if I look at the registers again, we're about to start the second iteration of the loop, right? And so what's going to happen for when we go through it this time? What's x0 going to change to? 2. What's x1 going to change to? 3. And then x2 and x3 are going to stay where they are, okay, because we never change them. And the what's going to eventually happen to the negative flag? Okay, eventually it's going to get set 0. Okay, so maybe let's just let's just run through this a bunch. Oops. Okay. Okay, so right here, look what happens. Now we just did a comparison, and now look what the flags are set for. The Z flag is set, but the N flag is not because we subtracted and we got 0. Okay, will we branch? Will we go back through the loop one more time here?
Yeah.
Why?
Because that would be the equal to.
Because I set it as less than or equal to, not just straight less than. Okay, and so we'll go back through the loop one more time. Okay, and now we're subtracting 5 from 6, basically, which is neither negative nor 0. So the flags aren't set. Yes.
Are the SP, PC, CPSR, are those all registers?
Yes.
How many registers are there?
Okay, so there are basically 32 general purpose registers. Okay, now I'm kind of lying because register number 31, right? Because it's 0 through 31 is 32 total. Register number 31 has sort of a weird dual purpose. Depending on the context, register 31 either is the stack pointer or is the uh, um, the 0 register. Okay, so it depends on if I call something XZR or SP for stack pointer. Okay, all right. Now there are also a couple of registers that are sort of specialized things that you can touch and use in a more limited fashion. Okay, like the program counter or the uh, the processor status register. The FP ones, what are those? Those are floating point registers, which since we're not doing anything that involves floating point, right now nothing's going on there. Okay. Now, when we do floating point stuff, then yeah, we'll have to pay attention to those. Yeah, so uh, what this is why I've been careful to say general purpose register, meaning that registers that you're allowed to do stuff with. Okay. And depending on the architecture, sorry, I shouldn't say architecture, depending on the operating system. So if memory serves, Apple uses, right, because their stuff on iPads and whatnot is an ARM 64 processor. They use x18, and it's sort of verboten to touch that. Okay. Um, X29 and X30 are kind of special for reasons we'll talk about later. Um, and so actually look at X29 and look at the stack pointer. They're the same thing. Okay. And uh, X30 is called something else. It's called the frame pointer. We'll talk about that later. Um, but those are sort of special, which is why, as we're going to see, uh, in some subroutine calls, we have to store old values of those things onto the stack for future reference. Okay. Um, so this would be what happens when you do a branch with link. Okay, which we'll talk about more uh, in a bit. Okay. Yes, Will.
How are your other programs running in the background controlling the loops?
Who knows? All right. And sort of the job of the operating system is to keep that show running. Now on the Pi, right, there are four processors, right? It's a quad core thing. Each core has its own set of registers. Um, and then, somehow the operating system keeps all this straight, or GDB as sort of being subordinate to the operating system here. How all that works, I have no idea, right? This would be why you would take a 300 level operating systems course at some point, which, uh, yeah. Um, so the let's see how to put this maybe a different way. If we were to run this thing sort of bare metal, if you will, okay, this would be to kind of like throw the operating system out the window and not have one. Then how many programs would be running? One, this one. That's it. Okay. Um, so maybe a better comparison for something like that would be when you've used an Arduino for anything. I know we used them in CS101 just for kind of silly purposes, but like, are you guys using them in AdLab or anything?
How you take it
Okay, well, fine. Mister, don't. I'm not taking AdLab. Okay. So anyway, an Arduino. So what's the difference between an Arduino and a Raspberry Pi? Well, several things, but
out? I'll do everything about it.
huh? There's no operating system on our Arduino. Okay. And also the processor architecture is a little different. And Arduinos, I think, are generally only 32-bit machines, but fine, whatever. Okay, so different architecture, different amount of RAM, but basically, when you load a program onto an Arduino, that is literally the only thing the Arduino knows is that program. Um, Whereas uh, on the Pi, right, we've got the benefit of an operating system and tools like this debugger and other stuff to um, to make our lives easier. This is one of many reasons why I settled on us using Raspberry Pis because we have all these tools um, to to help us. Okay. All right. So let me just kill the process ends and we're done. Okay. So does that kind of make sense then? How we did the branching in this case? Um, the We set this loop up to be less than or equal. We didn't have to. We could have set it up to be less than or whatever, right? That's up to you when you write the thing. Just what seems appropriate. Okay. The other thing I suppose I should say is when did we do the comparison here? Well, we did it inside the loop. Okay, fine. but we did it after we already had done some additions, right? So this is like if I had written what I wrote in C and had it compile it, it might have looked a little bit different, okay? Um, in particular, we did an unconditional branch right here, line 7, no, sorry, 8. We did an unconditional branch there, right? We had never done any comparisons to make sure that conditions were such that we needed to enter the loop. Why could we get away with that here? Well, because we just loaded in numbers and we loaded them in such a way that we knew that we would start the loop, right? So we knew as humans that this is going to be fine. If we were writing this in the midst of a bigger program, we might not be able to safely make that assumption. Okay, so we might have wanted to do a comparison um, between um, X1 and X2 before we entered the loop. Okay, so we could have changed this line 8 to be kind of like line 14 and 15, okay, to check whether or not we entered the loop before we do so. Okay, and in this case, it didn't matter because we kind of pre-cooked things so that we wouldn't have a problem, but in theory, we might want to elsewise. Okay, does that make sense? Hopefully. Question, preguntas, and or fragens. Jack, how you doing? All the way from, I don't know which city you're in. Near to Shanghai?
Yeah.
Okay, sure.
What's the point of doing this again?
The listing file. Okay, good. So let me actually quit the GNU debugger. So if I do, oops. The purpose of doing a listing file is so that you can see this. Okay, you already know what the instructions are because you were the one that wrote them, right? Um, but what it allows you to see is all the opcode business, right? So, um, so like I guess this was last time or the time before when we were saying, okay, how do you load -1 into a register when all you can load at a time, an immediate, is a 16-bit thing, and you need a 64-bit thing. So what are you going to do? Well, in order to do that, I had to know what machine instructions were actually getting used, and the listing file is what tells me that. Okay. Now, the one annoying thing, what's the annoying thing about the listing file? Or an annoying thing? Huh? All the red. Okay, fair enough. And that's only because I'm loading this in the console. If I loaded it in a text editor, that wouldn't be there. Okay, so what's an annoying thing about the machine instructions? They're all in the wrong order, right? It's the Indianness thing. Okay, so let's take the very first one, right? The very first instruction, yeah. Okay, how do I have to interpret that for looking it up in the spreadsheet? D2 800000. Okay. What about the one on line 7? I'd have to interpret that as D2 800023. Okay, because you take it one byte at a time. Within each byte, you don't flip the order. Okay, is that all right? Um, sorry, them just suck it up and deal with it, right? You guys are men. Yes. Okay. So excellent. So yeah, so the reason we use the listing file is because if we want to figure out exactly what instruction is being done, right, then we can look at it and then compare it to the stuff in the spreadsheet slash the dev manuals and figure out exactly what instruction we're dealing with. So we needed to do this because, well, for the particular move immediates that we've got here, so lines 4 through 7, we're loading in positive numbers or 0 in one case, right? So those all turn out to be the exact same kind of instruction. But what did we see when we were loading in -1? We actually were really using the move in command, not the move z command, right? And that distinction wasn't obvious until we looked under the hood and really got our hands dirty with the opcodes. Okay. So yeah, maybe another thing to notice is look at the opcode stuff going on there for branch loop, B loop, and also for BLE loop, right? They look pretty much completely different, okay? And um, uh, to decode them, we'd have to bust out the manual and figure out what bits are which, okay? Um, yeah, because in the branch less than or equal to, there's going to be a couple things set. Somehow we have to encode that we want to do less than or equal to. Okay, that requires, I think there are 16 different options for the condition, which would mean there's 4 bits there. Okay, um, the opcode is going to be however many bits, and where we're jumping to is going to be however many bits. So um, and all of that will add up to 32 when all is said and done. Okay, good. Yeah, sure. Question? No? Or Gucci? Gucci. Jack, how we doing? Uh, or Porter, if you're there. Let's see who else in the chat today. We got Jack. Oh, there's Porter. Um, and some other random people, probably bots. So anyway, um, okay. So there's a good loop. Okay, so what would be sort of a natural thing to do here? Well, what was a loop program that we ran that you guys wrote before? The triangular number thingy, right? Could we doctor this up to make it spit out a triangular number? Okay. Yay. Guess what your an assignment is? That. Okay. So basically, yeah, it will be to rewrite the Brookshire triangular number program, but this time in ARM. Speaking of the triangular number program, a couple people asked me this. Um, so in the triangular number program, what was the sort of maximum number that I specified? I just picked 0A, okay, with 10, right? So this would go up to the 10th triangular number. Why did I pick that? Simply because on Brookshire, it's a 8-bit machine, right? So what is the 10th excuse me, what is the 10th triangular number? Think 55, right? 10 times 11 over 2. Do you guys know the formula for the triangular numbers, by the way? Oh, this is really handy. Um, no, because you couldn't have used this on Brookshire um, because well, here, let's just go to the bastion of all knowledge of Western civilization, namely Wikipedia. So they're called triangular numbers for a reason.
Is there any application with triangular number?
Oh, yeah, number theory.
Okay.
Yeah. Okay. So they're called triangular numbers because of this, right? If you 1 plus 2 plus 3, it, makes a triangle. But the formula for them is this, right? So this is really handy, and there's actually a fun story to this that Gauss, when he was a kid, he's in like elementary school kind of thing, and his teacher got upset with the class, and so he's like, "Fine, I want you guys to sit down and add the numbers from 1 to 100." Okay, what's a really bad way to do that? 1 plus 2 plus 3 plus 4, right? So what did Gauss figure out? How to do it like that. But what he realized was, okay, if I'm adding 1 and 1 up to 100, let me think of it as 1 and 100, that makes 101. 2 and 99 makes 101. 3 and 98 makes 101. How many pairs are there? 50, right? Because I've got the numbers 1 to 100. There's 100 of those, and I'm pairing them off, so that means I've got 50 pairs. So if each pair adds up to 101 and I have 50 pairs, then the answer is 5,050. Done. And he went up to his teacher with the correct answer, and, after 10 seconds, and that was his teacher's like, this one's got some math talent. Okay. Um, yes, but anyway, so that's what that formula is basically expressing, is that you're pairing them up. That's why there's the division by 2, and each pair adds up to something, and you have however many pairs, right? So the Brookshire program, we did it exactly the bad way, which was to actually count up 1 plus 2 plus 3 plus 4 and so on. Okay. And in the assembly, that's what, for the ARM version of this, I want you deliberately to do that, even though you wouldn't want to in practice. Okay. However, there's another way to calculate them, which would be this. Okay. Now, how do you calculate that on the ARM processor? Well, there's an operation we have, two operations we haven't talked about yet, namely division and multiplication. Okay. So the division, well, actually, let's start with the multiplication operation. We were not able to use this trick on Brookshire because is there a multiplication instruction in Brookshire? Nope. Some of you guys had the joy of programming such back when you took 101, right? Who who of you did the multiplication project in 101? I don't remember who did which ones. Okay. And some of the rest of you guys did the greatest common, uh, the GCD algorithm. Okay. I try to switch it up every semester just for fun. Okay. So the reason you had to do all that in Brookshire was because there was no hardware multiplier or instruction to do multiplication. So you had to write the routine to do all of that stuff, right? And there were different algorithms that you could use to do it. Do you remember which one you guys used? Did you do Russian peasant method? Did you do quarter square? Any of these ringing a bell? Ding ding. Okay, Russian peasant method. You remember what you did? So that would have been the quarter square, probably. So, okay, there were different algorithms to do it, but you were doing it in software. The ARM architecture has a hardware multiplier, both for floating point and integer. That's nice. Okay, it's not the 1980s anymore. We have real processors, okay, that do have hardware multiplication. So there is, just like an add command, there is a mul command for multiply. Okay, and for that matter, there is a division command. What's the danger with the division command if you're working in the land of integers? Hmm? Yeah, fractions don't exist, right? So if I had the number 3 and I tried to divide it by 2, what's the problem? as an integer, I can't do that, right? Um, I would probably end up getting 1 out of that or an error, one of the two. Um, okay, because division of two integers doesn't always return an integer. Just it depends. Okay. Um, okay. So what's another way we could do division though in this one instance? Because we're dividing by 2. Yeah, we can bit shift, right? So we can do a logical shift to the left, or excuse me, to the right. Um, so in base 10, what happens if you shift all your digits, but you leave the decimal point where it is? If you shift all your digits to the right one spot, but you leave the decimal point, what have you just done? You divided by 10. And if you go to the left, you've multiplied by 10. Well, in binary, what happens if we shift one way or the other? We're either dividing or multiplying by 2. Okay. With remainder, right? So we discard um, yeah. Okay. So in this instance, right, we could handle the division by 2 not with the division operation, but rather with a bit shift. Which one's faster? Bit shift by far. Okay. Bit shifting is super fast. Now, um, for this particular formula, if we actually use the division operation, if we did the multiplied out the top and then divided by 2, not using bit shifting, we would have no issues. We would not have, the division would be fine because the number on the top there is always even. Why? Okay, or here maybe is a better way to put it. Why is it that that division by 2 will never cause a problem in this particular formula? There's a couple ways to think about it. All right, the number n is an integer, correct? That number could either be odd or even. Well, whichever one it is, what's the number n plus 1? The opposite. So no matter what n is, exactly one of the two numbers, n or n plus 1, is even. Hence, when you divide by 2, it's no problem. Right? Now, which one's even? Don't know. Frankly, don't care for right this instant. One of them's going to be even. And so hence the division by 2 isn't going to be an issue. Yay. Isn't number theory great? Yeah. How many of you guys have taken Math 108? Yeah. This all rings a bell, right? Divisibility and what about Math 219? Anybody? Anybody? Bueller? Yeah. Combinatorics. Yeah. So, okay. Anyway, so yeah, so that'll be a fun assignment is to recode the Brookshire stuff, but this time deliberately doing it the silly way, which is to not use this formula. Okay. All right. Is that okay? Huh? The multiplier? Well, you could use it to check, but I still want you to write the loop the long way. Just because, not because you would ever do this in practice, but because it gives you a sort of an obvious thing to loop with. Okay, now on the Brookshire one, I said make the number the triangular number, so this would be the number n here, go up through 0a, the number 10, okay? And I only did that because the 10th triangular number is 55, and when you start to get bigger than that, like pretty quickly you're going to hit 128, right? Or 127 actually, and then you would have overflow on Brookshire. Um, you're not going to have that problem in ARM because you've got 64-bit integers that you're working with here, right? So you could ask the machine, what's the 10,000th triangular number? And It'll take a minute, but it'll do it, right? Um, so, but the point is that your code should be written general enough that it doesn't matter what number I stick into it, right? So the way I would check this is uh, I'd go into your source code, right, and say, all right, one of your so like this number here in our silly loop program was set to 5. What about if I choose to change that to 30 or something, right? Everything should run exactly the same way. It just might take a little bit longer. Okay. So when you guys are testing this, change that number or wherever you, whatever register it's in, right? So that you can see whether or not it's spitting out the correct sequences of digits. And for something like the triangular numbers, you can obviously just check them against the Wikipedia or something to make sure that you're getting the right sequence um, out. Okay, does that make sense? Now, later, we'll actually doctor this up a little bit. So here, I've hard coded the number 5 into the program. Or, I could have changed that to whatever number. What would have been a more elegant way to handle that? Okay, you would have done this in Java. Yeah, prompt the user to type in a number. Okay, well, we can do that in assembly, and we'll talk about how to do that. Okay. Um, what's the danger of doing something like that, though? Right. Okay. That you have to do input like format validation, right? So if you prompt the user for an input and the number types or the user types in something silly that's not a number, you need a way to reject that and demand that they re-input something that is a number, okay, or the program's going to croak. Okay. So you'd have to do input validation of some sort, which we can also do. Um, but yeah, so in order to handle things like that, we're going to use two subroutines from the C standard library, printf and scanf. Okay, so printf is how we'll print information to the console, and scanf is how we'll get input from the user. Okay, um, but we still need to talk about those because of how they work. All right, so I think actually that would be a perfect spot for us to start talking on Thursday is with print and scan it. Well, we'll start with printf because it's a little easier to start with. But what this will mean is we'll also have to start talking about what are called the calling conventions. So which registers can you assume don't change when you go to a subroutine and which ones can't you? Okay, and that'll be important. So. All right, so we'll quit the stream here. See you guys Thursday. Have a good rest of your day. See you, Jack.